In this video, we're going to take a look at the substitution rule. Basically, we're going to encounter lots of functions where we need to integrate them, and most of the time the integral isn't going to be immediately obvious. It's not going to come from that list of antiderivatives or list of integrals that we had in the previous section. But we're still going to need to be able to compute these integrals. So one of the approaches, and this is typically the first one you should try, is called the substitution rule, or more commonly it's referred to as just U substitution. There will be other techniques, something called integration by parts, partial fraction decomposition, trig substitution. There's going to be a bunch of other techniques, and you'll learn those techniques in calculus too. But for now, we're just going to focus on this first technique, and the rest of them you'll learn next semester. So the substitution rule it allows us to, so again the question is, what if we need to compute an integral that isn't immediately obvious? And in this case, let's look at an example of something like this. Maybe I want to compute the integral of 2x e to the x squared dx. So this is definitely not in that table from the other day. It's a complicated thing. You can see that it's a product of multiple different functions. It turns out in this case, this is one that's going to work with the U substitution method. So in this case, what we're going to do is introduce a new variable. We're going to substitute from x to a new variable u. So we need to introduce a new variable. And again, the typical letter that we use will be the letter U. That's why it's often called U substitution. You don't have to use U. You could use another letter, but use the most common. We're going to introduce a new variable, U, to make this thing a little bit easier. So, to go through this problem hypothetically, let's say I want to let my U be equal to x squared. And in this case, the reason that I'm picking this is x squared, that shows up in the power of that exponential. So this is the power of the exponential. And there may be other things you can pick. If this is what I'm letting u be, and I want to eventually write this entire integral in terms of this variable u, so right now this would become e to the u, I would still need to figure out how to replace this x here and this dx here. And the way that we do that is by trying to take some derivatives so we can find what that differential is. So for example, du dx is going to be 2x. So I literally am taking my expression for u and I'm taking the derivative to find what du dx is. And then I can multiply both sides by the differential dx, and I can split this into du equals 2x dx, which is our new differential. So this is the differential du. And so notice we got lucky here. We already had a 2x and a dx showing up in the integral that we wanted. So if we go in and substitute all of these terms in, so subbing everything into place, so subbing in all the u's and the u related terms in place of all the x's, we get a new integral. And that integral looks like, so I'm still going to have my integral symbol, that e to the x squared part, that's going to now just be e to the u, right? Because x squared is u. And this part, the 2x and the dx, well, we see that right here, 2x and dx. Let me just underline the pieces that we've subbed in. The 2x and the dx, that's just du. So we can just rewrite this whole piece, this 2x and this dx, I can just rewrite all of that as a du. And this is an integral that we absolutely can compute. This is the integral e to the u du. Well, what's the integral of e to the u? Well, it's e to the u plus some constant. And then all we need to do is get our answer back in terms of the original variable. So back in terms of x, what do we have? We have that this integral, which we started off with, which was the integral of 2x e to the x squared dx, after making that substitution, this whole piece was equivalent to this whole piece. Its integral is just e to the u plus some constant. And what is e to the u? Well, subbing back in for x here, that's just e to the x squared plus c. So this is our answer. This was an easy integral. We've converted it from something that, just to make it clear, this one is an easy integral. So this one is easy. It showed up in that table. Back in section 5.4, whereas this one is hard. And it's not in that table. So we did the reverse of these. We took the hard one and we converted it into an easy one, one that we know off the top of our heads. And that's the goal of dealing with this U substitution. So this is what our answer winds up looking like. So I want to think about a couple of the things that happened as we did this to give us some hints of what we should be looking for. When is this going to work? As I mentioned a minute ago, we kind of got lucky in this example that when we found our du term, it just so happened that that du term, the 2x dx, where's my mouse? There it is. It just so happened that I already had these terms sitting in the original integral, so it made it really, really easy. In general, what we're looking for is, as we go through this, once we make our substitution, we will then take the derivative of whatever that substitution is, just like we did here, to solve for what the new differential is. If I want to replace dx with du, I need to rewrite what dx is by taking the derivative du dx and solving for du, or solving for dx rather, however you want to do it. We'll go through this process a little bit more. Long story short, what we're looking for are portions of the equation where some function shows up and also the derivative of that function shows up. So here we had an x squared showing up. We also had a 2x showing up. And even if there wasn't the 2 here, I can always force an extra factor of 2 to show up there and put a factor of a half out in front to cancel out for it if there wasn't a 2 there. So basically, if I have an x squared, I'm looking for something that involves an x. If I had an x cubed, maybe it'd be nice if I could find an x squared here. If I have a sine somewhere, maybe I have e to the sine of x, it'd be really nice if I had a cosine sitting out here somewhere. These are the types of things we're going to look for, pairs of a function and the derivative of that function. If you spot a function in here and its derivative, that's a good bet to use U substitution on. So let's take a look at some more examples to kind of, again, see how this is going to work in practice. Let me write this one down. So, and in fact, let me write down what I just said. So notice, well, often look for both a function and its derivative. In the integrand of what we're trying to compute. So if you see that, this is a hint to use this substitution approach. Okay, now let's do an example. Maybe I've got the integral of the square root of 3x plus 2 dx. This is not something that showed up in that table, but it's going to be fairly easy to do anyways. In fact, there's going to be more than one approach. So I'm going to do this problem a few different ways. So let's do approach 1 here. I'm looking for a function and its derivative, and I don't see one here. If I look inside the square root, for example, there's a 3x plus 2, and what is the derivative of 3x plus 2? Well, that's a linear function. The derivative would just be a 3. I don't see a spare 3 sitting around here. But whenever it's just a constant like that, I can always just force that spare term in. So let's try this. I'm going to let u be equal to everything inside that square root. I know how to integrate the square root of u if that's all that's sitting there. So I'm going to let u be 3x plus 2. And that tells me when I take du dx, I just get 3. And so if I'm looking for the relationship between these two differentials, du and dx, I see that du is equal to 3 dx. So I'm going to force that 3 in there, even though it's not in the original problem. I'm going to put it there. I'm going to have the integral of the square root, put this in the right place, square root of 3x plus 2, and I'm going to force a 3 dx here. So now I have something that looks like the du that I want. So I have something that looks like this piece here. But this is not the same as what we had here. This is 3 times larger. I've arbitrarily multiplied by 3. To make up for that, I'm just going to multiply by a third. And now I've effectively just multiplied by 1. I multiplied by 3 over here in the numerator, 3 over here in the denominator. This is just 3 over 3. I changed the form of it by multiplying by an especially convenient form of the number 1. And now what I've got right here is my u, and right here I've got du. And this whole equation, or this whole integral rather, just becomes 1/3 times the integral of the square root of u du. Here's my du. Here's the u. It's just the stuff inside the square root. That's what my u is. And I had this extra factor of a third that you can think of as some sort of like correction term. And this will work. Whenever you're doing a substitution where your u winds up being a linear term, the derivative is always going to be a constant. The derivative of any line is a constant, and you'll be able to do this little trick that we did here. So what is the integral of this piece over here? Well, that 1/3, again, is just sitting there. So I'll write it out in front. You can think of this as being raised to the 1/2 power. So if you prefer to write it this way, let me just write it like this. Maybe this will be easier for some people. And you can think of it as the power rule. I'm looking for the function whose derivative is u to the 1/2. Well, that'll have a power 1 larger than this. So that is going to be, I have my 1/3 there. I'm going to have something u to the 3/2. When I take the derivative of u to the 3/2, this 3/2 will come down and the power will decrease to the 1/2 that I was hoping to get here. But this 3/2 will come down, and I don't want a 3/2 there. I need to take that 3/2 into account by multiplying by a 2/3. There is what the integral of u to the 1/2 looks like. It's 2/3 u to the 3/2. And now when I take this derivative, The 3/2 will come down, it'll cancel with the 2/3 and leave me with the coefficient of 1 that I have sitting here. And the power will reduce from 3/2 down to 1/2. So this is what it looks like. And when we finish the problem, I guess I've got a little bit of room here, so I'll just sneak it in over here. This is now just going to be, well, I want to do a couple more lines, so let's write it down here. This is now 2/9 times u to the 3/2 plus c. And remember, our original problem was in terms of x. There was no u. We're the ones that introduced a u, so our final answer better not involve u. The original problem didn't involve u, it involved x. Our final answer better involve x, not u. So we need to convert back. So this whole thing is just going to be 2/9, substituting back in what we just found for our substitution. U is 3x plus 2, and that's raised to the 3/2 power plus c. So there's our final answer. That's what this integral looks like. This is my preferred approach in general, where I kind of do this correction factor and just figure out what is the appropriate correction factor that I would need to plug in to cancel out this 3 that I arbitrarily introduced to force this thing to look the way I wanted it to look. But let me show you a method where you don't have to guess that correction. This method isn't quite as foolproof, but it works most of the time. It's easier to make mistakes with this method, in my opinion. So I'm going to do the same thing. I'm going to make the same substitution. I'm going to let u be equal to 3x plus 2, and I'm going to get the same du dx out of this. So du dx is 3. And instead of solving for du as I did here, I want to go a step further and actually solve for dx, because that way I can just substitute in directly into the original equation. I can just replace this dx with whatever it is in terms of u. So this step isn't going to be any different. I've got that du is equal to 3 dx. I got that by just multiplying both sides of this equation by dx. And now I'm going to solve for the dx instead of the du. So dx, if I get this term by itself, means I need to divide both sides by 3. So it's going to be 1/3 of du, if you want to think about it like that. 1/3 du, or du over 3. And now, this is going to give us the 1/3 that I had to come up with as our correction, and it's going to give us that. We don't need to guess our correction, so no need to guess for whatever that correction term is. But again, this can lead to more difficulties down the line. Not going to worry about that right now. So substituting everything in, our integral is going to become, so we get, our original integral is the integral, again, of the square root of, let me just write it, it was 3x plus 2 dx, and we have now rewritten this as square root of u based on this substitution right here. I just replaced the 3x plus 2 with u, and now I just need to replace dx with what we solved for over here. It's 1/3 du, and I can pull that 1/3 out in front, and I've got the integral of the square root of u du. And now I have at this line the exact same thing that I had at this line right here. So let's do it in yellow. That line matches that line. The remaining steps would be identical. So I'm not going to repeat all of those. We get the same answer. So equals ... same answer, 2/9 3x plus 2 to the 3/2 plus c. Again, following all of, here's the ... these remaining steps. Okay, so there's two approaches that are basically the same. We picked the same substitution u in both cases. I prefer approach 1, where you kind of just think, kind of a guess and check method of figuring out what is the appropriate connection or correction rather, that I would need. I don't have 3 dx, I just have 1 dx, so let's just force that 3 there, and to account for the 3 that I forced there, I will correct for that with a factor of 1/3 out here. This approach bypasses that guessing game, but I do see this leads to more mistakes down the line, especially when people start doing definite integrals. So you're welcome to do it. It is just not my personal preference. A third approach is the following. What if we'd picked a different u from the beginning? So at the beginning, we picked u to be just what was inside the square root. What if I picked the whole thing? Well, sometimes we get lucky and picking a different u will also work. So I want to take a look at this. So I'm going to let u be the entire thing, square root of 3x plus 2. So this is a little bit uglier. What does that mean du dx is? So I got to take the derivative. We're going to have to do chain rule on this. You can think of it as 3x plus 2 to the 1/2 power. So I'm going to get, or just stuff to the 1/2 power. So I'm going to get 1/2 stuff. Oops. 1/2 stuff to the negative 1/2 power times the derivative of the stuff, which will pick up an extra factor of 3 there. So that is our derivative. And if I simplify that, clean it up a little bit, I can rewrite that 3 in the numerator, the 2 in the denominator, and I could write that as 1 over the square root of 3x plus 2. So that's what du dx is. What that implies is du is going to be equal to, multiplying both sides by dx, 3/2 1 over the square root of 3x plus 2 times dx. All I've done is take this expression du dx equals this, and I multiply both sides by the dx. So du is equal to this whole thing times the dx. Okay, and if we want to do kind of the same approach we did with method 2, if you wanted to, you could solve this for dx if you'd prefer. We could find that dx is instead, so if I wanted to solve for this, I need to multiply both sides by this square root of 3x plus 2. And to undo this, I need to multiply by 2/3. So we'll get 2/3 square root of 3x plus 2 times du. So again, I solve for this by multiplying both sides by the reciprocal of this. This right here is just the reciprocal of this. And so we found out what dx looks like exactly. And putting these together, if you think about it, what we just found is this whole piece right here is u again, and we wind up with, so we got really lucky in this case. This is not a case that I would generally recommend doing it this way. Oh, I meant to write approach 3, third approach. So what do we get? Our integral of the square root of 3x plus 2 dx is based on the substitution that we just made. It's going to be the integral of this whole thing is just our u, and dx we just solved for. Dx is equal to 2/3 of u du. So times 2/3 u du. So real quickly, sorry, this dx over here, right here, that thing is the 2/3 u du. And that's how we got this piece. So if I clean that up a little bit, I can pull the 2/3 out in front. This is just going to be the integral of u squared times du, which looks good so far. What is the integral of u squared? Well, that's going to be 1/3 u cubed plus c. And plugging in for what u was, we wind up with, cleaning this up a little bit, that 2/3 times the 1/3 is going to be 2/9. And our u cubed in this case is going to be the square root of 3x plus 2 whole thing cubed plus c. And if I rewrite this as a fractional exponent, I can rewrite that as 2/9. We're cubing it, we're also halving it, so that total power is going to be 3/2. So this is going to be 3x plus 2 to the 3/2 power plus c. And we wind up with the same answer that we got in our previous approach. So this third approach is in general. In my opinion, we got a little bit lucky with the way that everything canceled out here. I prefer the first two approaches. I think they're more sensible things to pick for the u, is the stuff inside. Pick a simpler u, if at all possible, than picking a complicated u. That is my general recommendation. Okay, so this is kind of the idea here. I want to point out exactly what we're doing in all of this. So the approach that we've done, now that we've done a couple of examples and we've started to get a hang of it, I want to come back to this point I made here, that we're really looking for both a function and its derivative inside the integrand. And not all the cases are going to always have that, like this one here, but that's ultimately the thing that we're looking for. The reason for this is, it turns out, let me zoom back into close to 100%, there we go. So it turns out that U substitution, or often referred to just U sub, is really a backwards version of chain rule. We are undoing chain rule. Right? Chain rule is an approach that we have to take derivatives. This is going to be the approach that we have to undo that same type of derivative. So it allows us to undo a chain ruled derivative. Okay. So think about it like this. If our integral can be written as the following, so my integral is going to be the integral of some f of g of x. And we also have some sort of g prime of x dx. So we've got our outer function f. So we've got an outer function, we've got our inner function g, and we've got the derivative of that inner function. And lastly, here's our, obviously, our differential. If we've got all of this, all we need to do is let u be the g of x. And we can rewrite this whole thing as the integral of f of u du. That is the idea. So that is basically what the substitution looks like. So let me just do this as sort of a side note. So for this side note, I want to think about this same problem from the perspective of taking a derivative rather than an integral, because again, derivatives are kind of easy. Integrals tend to be quite a bit more difficult. So I want to let capital F be a function. Such that if I take f prime of x, we get lowercase f of x. And then I want to consider what would happen if I had to do a chain rule on this capital F. So consider I want to take now d dx of f of g of x. Okay, so I'm taking the derivative of this big capital F, right? The same thing I'm trying to do here, but f is no longer a function of just x, f is now a function of g of x. So how do you take that derivative? Well, you would take the derivative of the outer part. So what's the derivative of f of stuff? It's just going to be whatever f prime of that stuff is, times the derivative of the stuff, so times g prime of x. That's what that derivative looks like. But recognizing that we are calling this the lowercase f, this is the same as f of g of x times g prime of x. Okay, and now I want to basically just use our fundamental theorem of calculus to basically say what happens if I'm trying to take the integral of d dx of f of g of x, and we need our differential dx there. So basically I've taken this whole line and it's sitting right there. I've just added in this piece and this piece. I'm taking the integral of that. Well, what happens when you take the integral of our derivative here? So this is, again, just to be clear, we're now taking the integral of, let's rewrite that, sorry, of, now I'm going to write the next line, f prime of g of x, g prime of x, dx. So again, the blue pieces are the pieces that are new. I've just taken this whole line, which was equivalent to the red part, right? This yellow part was equivalent to the red part. I've just done that substitution here as well. And at the end of the day, what does that give me? Doing now, call it the green part here in a minute. That's just f of g of x, got them all, g prime of x dx. Where again, blue parts, we're just integrating something that is now, let's make it green, this part, which is the same as this part. So I have this expression. This piece is the thing that we are trying to compute over here, but at the end of the day, looking back at it, it's just the same as this. What happens when you take the integral of a derivative? Well, this whole thing, this whole piece, is just the integral and the derivative essentially undo each other, so to speak, and we just get f of g of x. Oops, let me rewrite that. There we go. So this whole thing winds up just looking like this. That's that whole piece. If I copy this whole piece down over here, this is essentially what we're looking at. You just get back whatever this new antiderivative of the outer function is, right? You wind up with just dealing with that one single integral. You could think of it back up here. This piece up here is really that integral. That's just going to be our capital F. And in this case, it's going to be f of u. And that's exactly what this piece right here is. This piece is the same as this piece here, right? Because g of x was what we let be called u. If we know how to take the antiderivative or the integral of this outer function f, then we're in good shape as long as we've set everything up in this particular way. But this direction is what chain rule looks like, as you take the derivative this is what how chain rule happens. What we're trying to find is spot something that looks like the result of a chain rule and integrate it. And when we integrate it, we're going through this instead of, so just to be clear, as we take a derivative, right, here is the result of taking chain rules going this direction. Here is our end result of that chain rule. When we do U substitution, we're going to try to work this backwards, right? And we're now integrating this thing that involved a derivative, and we're trying to integrate something that looks like the result of chain rule. We're integrating, the blue part, something that looks like the result of chain rule, the green part. And how do we do that? All we need to know is how to find the antiderivative of this outer function, as long as we found the appropriate substitution to make. But again, these are the pieces we're looking for. We're looking for both a function and its derivative to show up somewhere in the thing that we're trying to compute. So this is it. This is essentially our big, ugly substitution rule. If we want to write it out clearly, again, I think it's really easier to just understand it by, in terms of dealing with, in terms of actually doing examples. I think it's easier than trying to understand the formula. But that's the idea. We've got this whole thing set up. At the end of the day, this f of g of x really just looks like f of u. And this piece over here is really just supposed to be the integral of f of u du. Right, based on all the stuff that we just set up here. So this is just the result of chain rule. That's just what chain rule looks like going in that direction. Okay. Hopefully that makes some sense. Let me write this out a little bit more formally. So what is our substitution rule? If u is some function g of x that we've got in there, and it's a differentiable function, because we're going to have to take its derivative in just a minute, whose range, so the function has a range, output values of u, is an interval, so its range falls somewhere in this interval I, and the outer function f is continuous on that interval I, then our integral f of g of x times the g prime of x dx can just be written as the integral of f of u du. These are just sort of the technicalities up here. Basically all we're saying is this g of x better give outputs, that's its range, that are valid as inputs of f. If g is spitting out values of u that don't work as arguments of f, then this doesn't really make any sense. So f of g of x needs to be able to make sense. We need to be able to apply f to the outputs that g of x spits out and have them be valid inputs of f. That's all this top line is saying. So this is our substitution rule, and this is why we're looking for both a function and its derivative whenever possible. So let me do another example, and we'll see what we can get out of this thing. So let's do a couple more. Let's try this one. Integral of the square root of 2 plus x squared times x to the fifth. That x to the fifth is outside of the square root. So let me try to make that hopefully totally clear. Okay, so looking at this, My guess is that the u that I'm going to use should be something to make this square root term a little simpler. Maybe it should be the 2 plus x squared. But if that's what I'm going to try to make my u, the derivative of this also needs to show up somewhere. And the derivative of this would wind up being a 2x. So I need an x somewhere. Well, I don't have an x. I have an x to the 5th. So maybe it would be smart to actually split this thing up. So if I'm thinking of this as going to be my u, that's going to imply that my du dx, which will actually compute in just a minute, maybe I should just do it, would be 2x. And that means that I need to look for something that involves that x somewhere else in the problem. And I don't have an x, I have an x to the 5th. So this is going to be our approach. Let's do that substitution, but let's break that x to the 5th, up into x times x to the 4th. So I'm going to anticipate that I want an extra factor of x, so I'm going to start by rewriting this as the integral of the square root of 2 plus x squared times x to the 4th times another factor of x dx. I've split that x to the 5th up so that now I am going to have the x, which will wind up being the derivative of this piece over here. And so now let's do that substitution. Let's let u be equal to 2 plus x squared. And if u is equal to 2 plus x squared, then du dx, its derivative, is going to be equal to the 2x, and du will be equal to 2x dx. So far, so good. Here is an example where I think it's better to do sort of our guess and check approach. I'm going to want to introduce a factor of 2 here that isn't actually here. I'm going to force a 2 right here, and to account for it, I'll put a factor of a half out here to make up for it, because otherwise stuff can get a little bit more confusing and difficult if we substitute in and try to do the other sort of more algebraic approach where we solve this all the way for dx. So let me make sure I've got all the pieces that we've got here. This piece is going to be easy, so let's see what we've got. So we've got the integral of the square root of 2 plus x squared, but that's just u, so that's the square root of u. And then we've got a factor of 2, so let me just go back and put it in right here. There's a factor of 2. I'll make up for it with a factor of 1/2 out front. So I've got this piece right here is my du, but I've also got this x to the 4th still sitting here, x to the 4th du. And this is a problem. I can't actually do this right now because it's got a mixture of u's and x's. I need to write this x. So we need x in terms of u. And so how do we find that? Well, we have our expression where we did that substitution. I just need to solve for it. So we need to solve u equals 2 plus x squared for x. And so to do that, I will subtract 2 from both sides, and then take the square root of both sides, and we will get that x is equal to the square root of u minus 2. And just keep in mind, there's both a plus and minus version of that value. Well, let's use the plus version for this particular case. Maybe there's some domain restriction that allows us to argue that we should only use the positive values of x. Okay, so here's what our picture now looks like. Now we've got the integral. So we get, going back and substituting that in, I've got this big ugly integral of the square root of u, x to the 4th, so it's going to be the square root of u minus 2 raised to the 4th, which is why it doesn't matter if we picked a positive or negative version to begin with, and we've got du. So again, all I've done is replace this piece with this piece. Okay. That's ugly, we just need to kind of clean things up. Oh, and I forgot my factor of half. I introduced that factor of half, remember, up here. I'm missing it both here and here. So there's what the answer looks like. So I'm going to start cleaning this up a little bit. I'm going to have this 1/2, the integral. I've got the square root of u. This term, when I raise it to the 4th power, is really just going to be u minus 2 squared du. And I'm just going to actually FOIL this out, and if we multiply this through, this is just going to be a big ugly polynomial at the end of the day with weird fractional powers. So I'm just going to multiply, so FOIL this piece out, and then multiply through by the square root of u. And I'll have just a big ugly thing where we can do a bunch of different power rules on it. So what do we get out of this? Again, I've still got my factor of a half. The integral of the square root of u, in fact, let me rewrite that now as u to the 1/2. And foiling that other piece out, I'm going to get u squared minus 4u plus 4 du. So that's just foiling this term that's squared out. We get this. And distributing that u to the 1/2 through, I'll get 1/2 times the integral of u to the 1/2 times the u squared will be u to the 5/2. Then from that I'll do minus 4u to the 3/2 and plus 4u to the 1/2 du. There's everything all foiled out together. Now I can actually compute all of these integrals. So I'm going to have my factor of 1/2 out in front. What is the integral of u to the 5/2? Well, I know the power is going to go up by 1, so it'll go up to 7/2. When I take the derivative of u to the 7/2, it would give me a factor of 7/2 that I don't want. So I'm going to multiply by 2/7 to account for that. The next term, I'll write down the minus 4, and now I'm just integrating the u to the 3/2. The integral of u to the 3/2 will be u to the 5/2. So u to the 5/2. But again, when I take the derivative of u to the 5/2, it'll pick up an extra factor of 5/2 that I don't want, so it's actually going to be 2/5 u to the 5/2. This last piece is going to be plus 4. The integral of u to the 1/2, the power will go up to 3/2, and when I take that derivative, I would pick up an extra factor of 3/2 that I don't want. So thinking of it in reverse, I will multiply by 2/3 to account for that, and then we need our plus c. Can't forget our plus c. So when this is all said and done, multiplying through, this 1/2 is going to cancel all of these 2's up in the numerators, and we will wind up with a big ugly mess that looks like 1/7. What is u? U was, going back to our substitution, u is right here. So I'm going to plug that in place of u. It's 2 plus x squared. So 2 plus x squared to the 7/2. Then I'll have minus, looks like 4/5 is the coefficient left over, of 2 plus x squared to the 5/2. And this last coefficient looks like I've got a 4/3 left over, 2 plus x squared to the 3/2 plus c. So there's the result of that. Alternatively, we wind up, I mean, I guess this is pretty much it. All I mean to say is when I say alternatively, you can do these problems coming back up to way back here. Again, this is going to be my preferred approach. You're always welcome to use this approach as well. And in general, I would not recommend doing this. Most of the time, this isn't going to work. Pick u to be something as uncomplicated as possible, but sometimes there's more than one choice of u that will happen to work, so I just want you to keep that in mind. But this is kind of your call. Up between these two approaches are the same. The only distinction, again, is whether I stop in solving for du in terms of dx, Or down here, I actually go a step further and I solve for dx in terms of du. So I can directly substitute in the dx into the original problem. Again, this approach tends to lead to fewer mistakes, in my opinion. So let me go back and just show you what that second approach would look like on this last example that we just did. So if I use the approach 2, where we solve for dx rather than for du. This problem would start with the same p's, our substitution, so we've still got the same integral that we're trying to do. It's still going to be, oops, let me remove that, it wasn't there. It was the integral of square root of 2 plus x squared times x to the 5th dx. And let's say that we were, again, smart enough to anticipate that it's going to be convenient to split that up into 2 plus x squared times x to the 4th times x dx. And we let our substitution be the same as before, so none of this is new. I'm letting u be equal to 2 plus x squared. And here's where things are going to slightly change. So we'll still find du dx, and it's still going to be 2x, and we'll use that to find du, which is going to be 2x times dx. But now we go one step further and we solve for dx, and we find that dx is equal to, in this case, du over 2x. And we immediately have something that involves a mix of both u and x, and I'm not going to be able to find an instantaneous way to deal with all of this. We can go back to the original problem, and writing it this way, we get our integral of, rewriting that first piece, it's now just the square root of u. We've still got this x to the 4th, and I've also got an x, and now I've replaced dx with du over 2x. And we try to cancel this with this, and this has given us an extra factor of 1/2 that winds up out in front of everything. We wind up with the square root of u, x to the 4th, du, by doing this cancellation. So this number became this number, and those two x's canceled, and we're still left with an x to the 4th, and we wind up now, at this stage, this whole expression matches what we wound up with at this whole stage back here. So there's the two things. We would still have to do the rest of the problem. It works. I just see a lot of people make mistakes at this stage when they wind up with something that involves both u and x, and they start canceling stuff. I see people do weird stuff here. So that's why I'm slightly warning against it, but you're welcome to do it. You just want to be careful. So they ultimately wind up doing the same thing. They have the same effect. Okay, I think I've knocked out most of these. Let's move on to doing this with definite integrals. So so what if we go back to dealing with definite integrals? So doing U substitution for definite integrals. It turns out this also is a little bit trickier. This is trickier because we need to be careful with those bounds of integration and what variable they're in terms of. So it's a bit trickier because we need to be careful with the bounds of integration. And we'll have two different approaches for this as well. So assume that we have the following. So here's our setup. If that g prime of x term, so if it is continuous on the interval AB, and AB are going to be our bounds, and if f is continuous on the range of g, so these are those same requirements I mentioned a minute ago. Then what does our integral look like? So now I'm suggesting is what we've got is integral of f of g of x times g prime of x dx, the same type of integral we've been looking for, one that involves a function and its derivative. But now we've got the bounds of integration a to b. And if you think about it, these values are in terms of x. What do we get when we do the U substitution? This is going to be equal to the integral of f of u du, and these bounds aren't a and b anymore. The bounds are instead g of a and g of b, which are values of u. Because, again, we're letting u be equal to our g of x. So what I mean is we've changed from the variable x to the variable u, and this changes the bounds. It changes, kind of transforms the whole picture. So this integral, we need to be careful when we deal with the bounds over here. We're going to have to either apply the variable transformation that we used right here, or we can keep the original variables but switch back to x before we actually do our function evaluation. So there's going to be two approaches. So let me just show both approaches. So and a lot of times, unless you get good in kind of anticipating which one's going to be easier, there's kind of a conservation of misery. They both require you to do some evaluations, do a little bit of work, but sometimes you can get lucky and one is an easier approach than the other. So let's take a look. I want to compute the integral from 0 to 2 of 1 over 2x plus 1 dx. So what should our U substitution be? Let me give you a minute to think about it for this particular case. In this case, what I would pick is recognizing that if this denominator were just a single value, if this whole thing were just 1 over u, I know how to integrate that. And the derivative of this bottom piece would just be an extra factor of 2. It's a constant. I can always add that extra constant in if I need to. So that's what I'm going to do. I'm going to let my u be equal to 2x plus 1, which gives me that du dx is just going to be 2, which tells me that du is 2 dx. And so I'm going to rewrite this whole thing as the integral from 0 to 2 of 1 over 2x plus 1, and I'm going to force an extra factor of 2 here, 2 dx, and to account for that factor of 2 that I added in, I'm going to put a 1/2 out in front of everything. So let me not crowd that. So there's the equivalent expression. And now I've got, again, this is just my du. This whole piece looks like a 1 over u. And we wind up with 1/2 times the integral of 1 over u du. But this is not going to be a 0 and this is not going to be a 2 anymore because those are not values of u. Those are values of x. We need to convert them to the values of u. So I need to do replace each of these two numbers with our substitution, basically. I need to plug into our substitution and figure out what is u look like when x is equal to 0 for the lower bound. So I want to know for these two numbers, I need to know what is u at 0, at x equals 0. So u, when x is equal to 0, u is equal to 2 times 0 plus 1, which implies that u is equal to 1. Oops, I shouldn't do an implication sign there. That's just an equal sign. There we go. And what is the value of u at x equals 2, which was the old upper bound of integration? Well, that's going to be u equals 2 times 2 plus 1, which is 5. And so these new bounds of integration are going to be from u equals 1 to u equals 5, whereas these old bounds are x equals 0 to x equals 2. So I'll often write in the letter x equals, or u equals to remind myself what are these bounds of integration given with respect to, which variable are they in terms of, just so that I can make sure I keep things straight and don't mix anything up. So now I'm going to do this integral. What is the integral of 1 over u? That's the natural log. So I've got my factor of 1/2. This is the natural log of the absolute value of u. And I'm evaluating it between, again, u equals 1 and u equals 5. And we wind up with 1/2 natural log of 5 minus the natural log of 1. Let me make it totally clear. What is the natural log of 1? Natural log function looks like, oops, this, and that is the point 1 right there. So it turns out this is 0. And I can ignore that term entirely. And we wind up getting that this whole thing can simplify to the natural log of 5 over 2. That's our answer. So this is our first approach. I guess I should have written that somewhere. This is approach 1. And now let's do approach 2, which I will also write. So, or I can start with the same thing, the integral from 0 to 2 of 1 over 2x plus 1 dx. And in this case, I'm never going to switch the bounds. I'm not going to evaluate at this stage. I'm not going to plug in the bounds in terms of u. I would instead convert back to be in terms of x, so I never have to change what these values are. I can still use the 0 and the 2. So in this case, we changed bounds to be in terms of u. Here I'm going to, in my approach 2, I'm going to keep the bounds in terms of x. Okay, so the whole rest of this problem, the beginning looks very similar. Let u be equal to 2x plus 1. We'll go through this whole process and we will get that our du equals 2 dx, the same that we did before, and we'll know that we're rewriting this equation as we'll pick up an extra factor of 1/2 out here. 1/2 the integral from 0 to 2 of, basically, let me make it totally clear that I'm going to be mixing variables when we do this. It's 1/2 the integral from, again, x equals 0 to x equals 2 of 1 over 2x plus 1 dx with an extra factor of, 2 dx. And this is our du, and this whole thing is 1 over u, and so we can rewrite it as 1/2 times the integral from x equals 0 to x equals 2 of 1 over u du. And this is what I mean. I'm mixing notation here. We've got the integrand and differential are both in terms of u, but my bounds of integration are still in terms of x. I'm going to perform this integration, and I'm going to get the natural log that we got before, but then I'm going to need to convert everything back to be in terms of x instead of leaving it in terms of u like I did here. So the result of this is I'm going to get 1/2 times the natural log of the absolute value of u, and we're evaluating that between x equals 0 and x equals 2. It looks exactly like what we got here, but in this case these bounds were in terms of u, and down here these bounds are in terms of x. So I need to rewrite this whole thing in terms of x. This is equivalent to 1/2 the natural log of the absolute value of, well, what was u? U was 2x plus 1. And that's what I'm evaluating between x equals 0 and x equals 2. And now when I plug those numbers in, I'll get 1/2 times the natural log of plugging in the upper bound, 2, we will get 2 times 2 plus 1. So I will get the same 5 that we got before. And then from that, I will subtract off this thing with the 0 plugged in. When I plug in a 0, I'll get 2 times 0 plus 1, and I will get 1. That is again 0, and we get the same result, the natural log of 5 over 2. Same result, two different ways. In approach 1, hopefully we can kind of see it all at once. In approach 1, I kept, I changed the bounds to be from in terms of x to being in terms of u. And to do that, I had to evaluate what u looked like at those two different points. Alternatively, in approach 2, I kept the bounds in terms of x. I never switched these bounds. They stayed 0, 2, 0, 2, 0, 2 the whole time through. But when I evaluated these numbers here, I had to plug into the same formula that I had to use right here to get the 1 and the 5 anyways, and it gave me the same 1 and the 5. So this is what I mean when I say conservation of misery. We can either do the work up here, or we can do the work at the end. Sometimes one approach is a little bit easier than the other, but oftentimes you're going to have to do the same amount of work. One thing that is kind of interesting, I wish I had an example off the top of my head, but I don't, is that sometimes when you make this substitution, I'll find an example before the end of the semester. I'll make sure we do one maybe on like the exam review. Sometimes when you plug in, you wind up getting the same bound. You have a substitution that works out so that you get the same bound. This often happens when you're dealing with trig functions that are periodic. So I plug in one x value and it spits out a number. I plug in a different x value, it spits out the same number. And whenever I'm taking an integral and these bounds are the same, the whole thing is going to be 0, because essentially you're evaluating, right, the area under a curve from this point to this point, and so it just winds up being a straight line. There is no width to it, and the area of the whole thing goes to 0. So that's one thing that can happen where it's better to do approach 1 than approach 2. I will find an example where that happens. Hopefully, if that doesn't make sense, I will try to bring it up later on when we come up with an exam review. The last thing I want to talk about are just some other useful facts. These are things that will make your life a lot easier. So these are things that they come up a lot. So one thing I want to think about is like integrals of symmetric functions. This is something you'll rely on a lot in Calculus 2, is using symmetry to make your life a little bit easier. So, let's suppose that our function f is continuous on whatever interval we're interested in computing the derivative of, of the integral of. So it's continuous on AB. And we have the following. If we're doing something that looks like this. Say part A. If f is even, meaning that f of negative x is the same as f of positive x. What is this integral going to be? Our integral from negative a to positive a of f of x dx. So maybe this was a bad interval to take. Let's not say a to b. Let's say it's continuous on at least from negative a to a. Let's say that. Negative a up to a. That's the interval I actually care about. Okay. So real quickly, I want to figure out what this is equivalent to. And I can do it pretty easily by just drawing a quick picture. Here is an example of an even function. Ooh, not quite. Whatever, close enough. Right, so basically at the point A and at the point negative A, that height and that height match. This is our even function. X, Y, and it's, let me write that below, this is even. I'm asking, what is this total area under here? Well, because of the symmetry, that total area is the same as just looking at this area and then doubling it. So that's what we're going to find out here. This is the same as just doing 2 times the integral from 0 to a of f of x dx. And this can be really nice because oftentimes plugging in a lower bound of 0 is much more convenient than plugging in a lower bound of like this negative a. 0 is often the easiest number to evaluate. Whatever this integral winds up looking like, whatever its antiderivative is, plugging in 0 is usually easier than plugging in any other number. So this can be a time-saving technique. And it's all geometrically because this red region, this region over here that's not red is a symmetric copy of it. So I can just find this red region and double it to find the total region under that curve. So that's part A. If our function's even, what if our function is odd? So if f is odd, which means that f of negative x is the same as negative f of positive x. That was our definition of odd. Well, in this case, if I take an integral from negative a to a of my f of x dx, and I want to know what it's equal to, it's going to be easy as well if we just draw our picture. So here's our picture, x and y, and let me give you an example of an odd function. Maybe it does something like this, and then it does something like this. And here is our positive a, here is the same value, negative a, over here. And the area that we're computing is the area from here up to here. So that region plus that region. Well, what is that integral going to be? In this entire region, it's negative. In this entire region, it's positive. But the shape is still the same shape. Right? That shape matches. Maybe do them in different colors here. They're the same shapes. One's positive, one's negative. What are they going to add up to? 0. So no matter what, we're going to get 0 when we integrate an odd function over this symmetric type of interval. Let me make it clear where that negative a is. I feel like it got covered up too much, so let's write it over here. Negative a. Okay, so if you're dealing with an even function, you can just find half of the area and then double it. If you're dealing with an odd function, no matter what, it's going to integrate to 0 because there's an equal amount of positive area under the curve as there is to negative area under the curve. We can prove these using these substitutions. I have that in my notes if you want to take a look at it, but it's not super important. What I want to do instead is show you something that's, I think, a little bit easier, or another interesting fact that I didn't put in my notes, and it has to do with trig functions. So this is, we just did integrals of symmetric functions. Now let's do integrals of sine and cosine. And this is a super useful thing that a lot of people, when I teach my differential equations classes and my linear algebra classes, these are things that they never learned, but they're really obvious. If I give you this problem, I want to know what is the integral from 0 to 2 pi of sine of x dx. Or for that matter, what is the integral from 0 to 2 pi of cosine of x dx? If we draw these and look at the geometric interpretation, both of the answers are really, really obvious. So here's my x-axis, here's my y. My sine function goes like, let me split this up, there's 2 pi, here is pi, here is 0. My sine function goes like this. There's a height of 1, down here would be a height of -1, and this is the area that we're trying to find. And exactly like we just saw in the case with the odd function, we have a region where we're going to have, I guess I'll do the colors matching the same way. So I'll have a region that's our positive area, that's this region, and then I have a region with a negative area, and that is this region. And the shapes are the same shape. One is positive, one is negative. What is this integral going to be? It's going to be 0. 100% of the time. And in fact, if we take any function like a sine or cosine and we integrate it over any number of periods, what if I did it to 4 pi? Well, now I'd have another bump on top, another bump on bottom, and they would still cancel out. So as long as you do a full period or any multiple of a full period of a sinusoidal function, you'll get 0. It works as well if I wanted to sneak a factor of like 2 in there. If I want to do sine of 2x, that just oscillates twice as fast. So it looks something like this by the time you get to 2 pi. Here would be 0. And you'd have the exact same result. Positive, positive, negative, negative. The overall integral would go to 0. So it doesn't have to just be sine of x. It can be sine of any coefficient you want to put in there. As long as you're integrating over a full period, it's going to integrate to 0. And the same thing is true with cosine. So think of with cosine, it just looks a little bit different. We start up here, go down, come back up to the top, and there's our 2 pi. But we're just chopping it up into kind of 4 pieces that match, if you want to think of it that way. Here are our 2 negative pieces, and here are the 2 equivalent positive pieces. Again, negative, negative, positive, positive. This is a height of 1, this is a height of -1, 0, 2 pi, x, y. The total area, adding those pieces up, is going to be 0. So this is another useful thing to keep in mind. It also works for other powers. What if I did sine cubed of x? Or sine cosine to the 5th of x? As long as the power is odd, the portions that are positive will stay positive, and the portions that are negative will stay negative, and we'll get the same cancellation. So this works not only on putting other coefficients next to the x, so doing sine of 2x or sine of 4x or something, but also doing odd powers of sine or cosine. So as long as you've got odd powers there, this same property will be true It's going to change what the shape looks like, but it's not going to change what's positive and what's negative. However, hopefully it's easy to anticipate. If I were to put something like a square here, that is not going to be the case anymore. Putting a square there, positives will stay positive, but the negatives will also become positive when you square something. So that doesn't work for even powers. So it also works on odd powers of sine and cosine, as long as we integrate over full periods. So that's the idea. So these are just a couple other useful facts that can help you down the line make hard problems into easy problems. I welcome you using any of these types of facts, for example, on the final exam. If you do something like this where you immediately say, oh, that's equal to 0, just put a quick little sentence or a phrase saying integrating sine over a full period or something like that, and I'll know what you mean by that. So if you use something like this, make sure you explain it in words, but I'm fine with you not actually going through the process of computing the antiderivative of this, evaluating at this point, taking the difference, and winding up getting 0. You can just use these types of arguments in all of these scenarios. So hopefully this is helpful. This is the last topic for us for the semester. I will come back and try to put a review together and go through that review in a lecture, and maybe I can even do it live with you guys, invite you guys to like a video conference, and we can go through that together. So that's my hope, and I'll try to get that stuff prepped so maybe we can do it sometime towards the end of next week. And obviously for people that wouldn't be able to make a live one, I will record it so people could watch after the fact. So hopefully I'll have that prepped for next week, but otherwise this is it, and hopefully this is everything you need to get through those homeworks and the last quiz. So good luck.